Okay, welcome to our second lecture on Laplace transforms. So this video is going to talk about some of the properties that Laplace transforms have and how we will need to utilize these properties in order to solve the problems we encounter in process control. Okay, so there's really some specific properties of the Laplace transforms that we need to know about and know how to use, and also a few tools that are relevant to Laplace transforms. So the first property is linearity. We're going to talk about linearity. Linearity is a really useful property, and it's really akin to the distributive property in algebra. The shifting theorem, so that's a Laplace transform property that will be really useful for us when we see time delays. So for instance, if you get in the shower and you turn on the shower all the way to hot water doesn't instantly come out. There's some delay in the time it takes that water to travel through the piping system from the hot water heater to your shower. So we encounter these types of signal delays frequently in process control, and we'll have to know how to deal with them when we encounter them mathematically. We also learn about the properties of derivatives and integrals when it comes to Laplace transforms, and then finally we'll practice some application of these properties to solve differential equation initial value problems. Additionally, there's an important tool that we'll often have to use when we take the inverse transform of some sort of transfer function, and it's called partial fraction decomposition. We will likely get to that in the next video. Okay, so to start out, these tables and a discussion can be found in your Kreisig text, which was the book you used for process analysis. So I encourage you to read more about it there if you need more information. So the first thing I want to mention is the linearity of the Laplace transform. So the Laplace transform is a linear operation. This is really useful because it allows us to kind of break some sort of function into its respective parts. So let's say we have some sort of signal that we receive from our system, and it's actually going to sum with another signal, and linearly. So we have some constant coefficient a multiplied by our function f, which is a function of time, summed with some other constant b multiplied by another function of time. Both of these represent signals, and the sum of these two signals is our dynamic equation. If we take the Laplace transform of this function now, so something like this, okay, we will end up with using this linearity principle to say, hey, this is actually going to be equal to just the same thing, the summation of these two signals now in the Laplace domain. Okay, that'll be very useful. It's also useful because we can see if we're going to take the Laplace transform of some function and there's a constant coefficient within that function, we can actually factor it out and not have to deal with it. It'll make it a lot easier to find those functions in the transform table. So the next principle is the shifting theorem. So this property of the Laplace transform is going to be especially relevant when we see signal delay in our process control problem. So often we'll see that there's some time it takes the signal to travel from whatever source to to our system. So in this case, we usually see some sort of time, for instance, t naught. For instance, we'll have some function x, and it'll be represented as a function of t minus t naught, where this t naught is actually the signal delay. So in this case, we're going to take the Laplace transform of this function, and the shifting theorem tells us that we can simply multiply the resultant function, the transform of x of t would be capital X of s, Okay, and we could simply multiply this transform function x of s by e to the negative st naught, and now we've accounted for that time delay. Very useful. Okay, so perhaps the most important property of the Laplace transform is the property of derivatives. So obviously we're trying to solve differential equations. There's going to be derivatives. We're going to want to approach these derivatives and solve them. So what's really cool, so we're going to take some derivative. So for example, let's say we have a term within our function, let's see, I'll use the same one, df dt, okay, a derivative term. If we take the Laplace transform of this differential equation, or differential with respect to time, we end up with now an algebraic expression. In this case, we can just take our Laplace variable s and multiply it by the transformed function f of s. In this case, we also will need to subtract the initial condition. Here, look, this is the initial condition in the time domain, so f of 0. So just like this, we can extend this principle to higher order derivatives. So you can kind of see how here, if we take the Laplace transform of the second derivative of s, we still have that function here. They're using this notation, the Laplace transform of f, little f. Realize that this is big F of s. This notation is kind of interchangeable, multiplied by s squared. We subtract the initial condition we saw in the first order derivative and multiply it by s. S times the initial condition of that function at 0 minus the initial condition of the first derivative at 0. Also very conveniently, and it's just important to kind of put together the pieces later, that often we will define process control problems in a way that the initial condition of the function and its derivatives are 0. That's very useful. And you'll find that these deviation variables that we talked about in the last lecture are really useful. They often result in the initial condition of the function and its derivatives all equal to 0. Okay, and for higher order derivatives, the same process continues to apply. All right, additionally, we can look to the Laplace transform property of integrals. So in this case, we can see that if we need to take the integral of a function from 0 to t, keep in mind, anytime we're talking about process control, we can only control the future. We can't control the past, so it doesn't make sense to talk about time less than 0. Anyways, if we're going to integrate some function, here tau is a dummy variable from 0 to t, we can represent this, the Laplace transform of this integral, as 1 over s multiplied by our transformed function capital F of s. Okay, so you can also see that this property works in reverse just as well. Okay, so we've summarized the properties. In the next video, we're going to utilize these properties in a few examples. Good luck!